We will now continue with our discussion on PV diagrams that we started in the first part of the lesson. Tell me, what does a PV diagram represent? Well, it is a plot of pressure against volume, and the area under the PV diagram represents what? It represents the work done. Okay, now here I have a situation. The figure here shows an ideal gas at a state P1, V1, T1. So at this point, the state of the ideal gas is P1, V1, T1. It now moves to a state 2. What is the state of the gas here? Pressure remains a constant. Pressure hasn't changed. Volume has changed to V2 and the temperature has changed to T2. Alright? So the figure shows an ideal gas at an initial state P1, V1, T1 and heated at constant pressure to a state P1, V2, T2. What is the work done during that process? The work done during this process is the area of the shaded region, which will be this pressure multiplied by the change in volume. What is the work done for an isobaric process? This stage is an isobaric process. The work done is pressure multiplied by the change in volume, PdV, which is the area of the shaded region. Now, the gas is now cooled under constant volume. Look at this. It is cooled under constant volume so that the pressure reduces to P2. The volume remains a constant and the temperature falls to T3. Tell me, what is the work done during this time? From state 2 to state 3. What is the work done now? Well, there is no work done. Why? Because work is done only when the volume changes. Since there is no change in volume there is no work done. So the work done during this stage is 0 since there is no work done. That means when a gas is taken from state 1, that is P1, V1, T1, to state 2, P1, V2, T2, to stage 3, P2, V2, T3, the work done is given by the area of the shaded region. Moving from state 2 to stage 3, there is no work done. Therefore, the total work done is the same as the work done during the first change. Okay. This figure shows the ideal gas. Now, let's go through another situation. Here is another situation. A gas is at an initial state, P1, V1, T1. It is taken through constant pressure. It is cooled at constant pressure to a state P2, V1, T2. Alright? From an initial state P1, V1, T1, the gas is cooled at constant volume to P2, V1, T2. Pressure changes from P1 to P2, volume remains a constant, temperature changes from T1 to T2. Tell me, what is the work done during that process? There is no work done. Why? Because there is no change in volume. Alright, now it is heated at constant pressure so that the state now changes to P2, V2, T3. Now, what is the work done during this time? Work done is the area under the graph. So the work done during this process is the area under the graph, and this is the total work done. If you notice, In the previous case, we took a gas from P1, V1, T1 to P1, V2, T2, and then to P2, V2, T3. It reached the same final state. The final stage in the previous case and in this case are the same. But in the previous case, you notice that the work done was a large quantity. But in this case, the work done is a very small quantity. So the path taken in a PV diagram is very important as far as the work done is concerned. Let's now talk about isothermal expansion. What is an isothermal expansion? What does isothermal mean? Well, a process that takes place at constant temperature. So an expansion, a certain amount of gas is allowed to expand at constant volume. Now, suppose I ask you, well, I want to ask you this question. What is the equation for an isothermal process? We derived an equation for it some time ago. You remember Boyle's law deals with isothermal process. What is the equation for Boyle's law? Boyle's law equation is P times V remains a constant when the temperature remains a constant. Well, when we talk about isothermal change, we don't need to say temperature remains a constant, because for an isothermal process, the temperature is a constant. So the equation for an isothermal process is P times V remains a constant. That is the equation for an isothermal process. I will ask you this again in the next class. Okay. Now, this is the picture that shows an isothermal process. The temperature remains a constant. You can see the initial state of the gas is P1, V1, T1, and it expands from an initial volume to a final volume at a constant temperature. The temperature does not change. The pressure changes from P1 to P2. In other words, the pressure falls. The volume increases, the pressure decreases. You remember this curve when we talked about Boyle's law? What do you call this curve? This curve has a name. This is the isotherm. So this is the isotherm of this gas that expands from a state P1, V1, T1 to a state P2, V2, T1. What is the work done? The work done is given by the area under the graph. You see, previously it was easy for us to calculate the area because the areas were rectangles. This is not as easy as that. So what do we need to do? We need to use the method of calculus. Since the temperature remains a constant, such a process is called an isothermal process. The work done in an isothermal process is given by the area under the PV diagram, and I can write it as, how can I write it? It will be integral V1 to V2 of PdV. Well, the same equation. Work done is integral V1 to V2 of PdV. But what is the difference? In the previous case, we considered the pressure remaining a constant, isobaric process. When the process is isobaric, the pressure remains a constant, that line will be a straight line. So you don't need calculus to measure that area. But in this case, you need to use calculus because pressure now is a variable. Volume is a variable and pressure also is a variable. So if you want to do this integral, you need to rewrite this pressure in terms of V. Can we do that? All right, let's see. We can go to our savior. You see the gas equation. PV equal to nRT, and we can solve for P from there. What happens? P equal to nRT over V. If you notice, nRT is a constant. Isn't T a constant for an isothermal change? Yes. So, because the change is isothermal, T is a constant, R is a constant, N is a constant. So, we now expressed P in terms of V. Let's take this value of P here. Therefore, what is work done in an isothermal process? Replace the P by nRT over V. Will be integral V1 to V2 nRT over V times dV. And we can now take the constant terms outside. nRT is a constant. So that will be nRT comes out integral V1 to V2 of 1 over V dV. Okay, how many of you recall this integral? What is integral of 1 over V dV? It's a very elementary integral that you do in your calculus 1. Is that right? Integral dx over x is ln of x. Integral of dv over v is ln of v. I hope you know that. See that? But integral of dv over v. So this is the standard integral. Integral dx over x is ln of x. Therefore, integral 1 over v dv is the same as dv over v is ln of v. So this integral is ln of v. That is nRT ln of v. Lower limit is v1. The upper limit is v2. What do we now do? Set v equal to v2, the upper limit, and then minus set v equal to v1. That will be nRT ln v2 minus ln v1. And use the properties of logarithms to write this as a single ln quantity. What is ln v2 minus ln v1? That will be ln of v2 divided by v1. And here is another important equation that you cannot afford to forget. Work done in an isothermal process is nRT ln v2 over v1. Take note of that. Work done in an isothermal process. Alright, let me ask you now, what is the equation for the work done for an isobaric process? The pressure remains a constant. Is P dV, P times V2 minus V1. Work done in an isothermal process, temperature remains a constant. Is nRT ln V2 over V1. Okay, let's do a small problem. 1 mole of gas initially at P1 equal to 3 atmosphere, V1 equal to 1 liter, and internal energy U1 equal to 456 joules is cooled at constant volume so that its pressure drops to P2 equal to 2 atmosphere. It is then allowed to expand at constant pressure until V2 equal to 3 liter and U2 equal to 912 joules. Show this process on a PV diagram and calculate the work done by the gas. Also find the heat added during this process. Alright, let's start. The figure on the right, here is the diagram of that. That is not difficult. What is state 1? If you look at the axis there, This is P, this is V. V is measured in liters. 1 liter, 2 liter, 3 liter. Pressure is measured in atmosphere. 1 atmosphere, 2 atmosphere, 3 atmosphere. Now, where is the gas in the beginning? What is its state? Its pressure P1 is 3 atmosphere. The pressure P1 is 3 atmosphere. Volume is 1 liter. So here is the gas in stage 1. Its internal energy is 456 joules. Now, its pressure drops to P2 equal to 2 atmosphere at constant volume. You notice that the volume doesn't change. It drops to P2 equal to 2 atmosphere, and then it is allowed to expand. From here, it is allowed to expand so that the volume changes from 1 liter to V2 equal to 3 liters, and the internal energy now is 912. So this is the PV diagram of the process. And what is the work done? The work done during that process is the shaded area. And can you calculate the work done? Work done is, this is an isobaric process, it will be P times V2 minus V1, which will be, the pressure is 2 atmosphere and V2 minus V1 is 2 liters, 3 minus 1. So the work done is 2 atmosphere times 2 liters, but you can't have those units. You got to change them to absolute unit. What will you do? Atmosphere is multiplied by 1.01 times 10 to the 5. So 2 atmosphere is 2 times 1.01 times 10 to the 5. Now this is in Pascal. And liters becomes meter cube when you multiply by 10 to the negative 3. There are 1,000 liters in a meter cube. So this now becomes in joules. Work done is 404 joules. Alright? So the work done during that process is 404 joules. What else do we need to do? Find the heat added during this process. Well, can you do that problem on your own? Find the heat added. What is the equation for heat added that we obtained in the beginning of the first law of thermodynamics? dQ equal to du plus dW. Is that right? We know dW, the work done. Do we know du, the change in the internal energy? Yes, we know. Original internal energy is 456 and the final internal energy is 912. Therefore, what is the change in internal energy? We know that. We know the change in internal energy du. We know the work done. Therefore, the heat added during that process can be calculated as dQ equal to du plus dW. Alright? So du equal to U2 minus U1, the change in the internal energy, which is 912, is that right? Minus initial internal energy is 456, and that is 456. Therefore, the heat added is dQ equal to du plus dW, that is 456 plus 404, that is 860 joules. Okay, so PV diagrams are very useful in calculating the work done, the amount of heat added, and so on. Let's do another one. 1 mole of an ideal gas at P1 equal to 3 atmosphere, V1 equal to 1 liter, and U1 equal to 456 joules is heated and is allowed to expand such that it follows a straight line path on a PV diagram to P2 equal to 1 atmosphere, a straight line, not horizontal. You see, from P1 equal to 3 atmosphere to P2 equal to 1 atmosphere along a straight line. P2 equal to 1 atmosphere, V2 equal to 3 liters, and U2 equal to 912 joules. Show this process on a PV diagram. Can you do that on your own? It's very simple. Okay, there you are. The initial state of the gas is P1 equal to 3 atmosphere, that's the pressure, V1 equal to 1 liter, and internal energy is 456 joules. It follows a straight line path to P2 equal to 1 atmosphere and V2 equal to 3 liters. Now that is the PV diagram. Show this process on a PV diagram and calculate the work done by the gas. Can you calculate the work done here? Well, you don't need calculus here. The work done is the area, and the area is made up of a rectangle plus a triangle. You see? And what is the area of the rectangle? This is 1 atmosphere and this is 2 liters. So the area of the rectangle is 1 atmosphere times 2 liters. Now, plus the area of the triangle. The base of the triangle is 2 liters and the height of the triangle is 2 atmosphere. The area of the triangle is 1/2 base multiplied by height. The work done is given by the shaded area, and the shaded area is made up of a rectangle and a triangle. Let's calculate those areas. The area of the rectangle is, the width is 1 atmosphere, the length is 2 liters, 1 atmosphere times 2 liters, and the area of the triangle is 1/2 base, 1/2 times 2 liters multiplied by the height is 2 atmosphere. So, total work done is 1 atmosphere times 2 liters plus, this will be 1/2 times 2, 0.5 times 2 liters times 2 atmosphere. That will be, look at this, 1 times 2, this is 2 atmosphere liter plus, this is also 2 atmosphere liter. That is a total of 4 atmosphere liter is the work done. Can you leave it like that? No, you need to convert it to joules. How do you convert that to joules? Convert atmosphere to Pascal multiplied by 1.01 times 10 to the 5 and liter to meter cube multiplied by 10 to the power of -3. There you are. And that gives the work done is 404 joules. Exactly the same quantity that we had in the previous problem. You remember that one? Okay. And therefore, what is the next thing we need to do? Find the heat added during this process. Well, the heat added during the process will be du plus dw. The change in the internal energy is U2 minus U1. That is 912 minus 456. That is 456 joules. Therefore, dq equal to dw plus du. That will be 404 plus 456, 860 joules. You can see the same quantities, although the parts were different. Okay, let's do another one. An ideal gas, initially at 20 degrees Celsius and 200 kilopar, you can see the pressure is now given in Pascal, has a volume of 4 liters. It undergoes a quasi-static isothermal expansion until its pressure is reduced to 100 kilopar. Now, what is a quasi-static change? A quasi-static change is a change, you see, isothermal, so that at every state of the change, the temperature remains a constant. In other words, the change happens in such a way that equilibrium conditions are established very quickly. That is a quasi-static state. So an ideal gas initially at 20 degrees Celsius and 200 kilopar has a volume 4 liters. It undergoes an isothermal expansion. That means the temperature remains a constant until its pressure is reduced to 100 kilopar. Find the work done by the gas and the heat added to the gas during the expansion. Now, before we go to the problem, let me ask you, do you remember the equation we developed for work done in an isothermal process? W isothermal, what is that equal to? Right? It is nRT ln V2 over V1. We might need that for this problem. Alright, let's pick the data. T1 is 293 Kelvin. P1 is 200 kilopar, which is 200,000 par. V1 is 4 liters. P2 is 100 kilopar. And we need to find the work done by the gas. Now, you can see how useful our ideal gas equation is. We got PV equal to nRT. So, if you look at the stage 1, we got T1, we got P1, we've got V1. Therefore, we can now find the number of moles of that gas. Why do we need the number of moles? Well, the equation for the work done contains nRT ln V2 over V1. We need the number of moles of the gas. So, you are given the value in state 1, you know the temperature, you know the pressure, you know the volume, therefore you can calculate N as PV over RT. P is 2 kilopar, that is 2 times 10 to the 5 Pascal. V1 is 4 liters, 4 times 10 to the negative 3 meter cube. Always keep the units in the right form. Divided by R is 8.314. Remember, when you use pressure in Pascal and volume in meter cube, the value of R is 8.314 joules per mole per Kelvin. And the temperature is 293 Kelvin. Very, very important to convert that Celsius to Kelvin there. And that gives me, you got 0.328 moles of gas. Okay, now if you look at the equation again, what is it that we are missing here? Work done in an isothermal process is nRT. We've got N, we've got R, we've got T, ln V2 over V1. We've got V1, we don't have V2. So what do we do now? For an isothermal process, what is the equation for an isothermal process? I'm going to cover that with my head. What is the equation for an isothermal process? PV is a constant. What does that mean? It means P1 V1 equal to P2 V2. Well, we know P1, we know V1, we know P2, therefore we can find the V2. So V2 is P1 V1 divided by P2. And now P1 is 200 kilopar, V1 is 4 liters, P2 is 100 kilopar. I haven't changed anything there because I left the pressure units in kilopar, numerator and denominator. I left V1 in liters, so that I will get V2 also in liters. So this will be 8 liter. I hope you understand why I did not write any units there. This is 200 kilopower times 4 liters divided by 100 kilopower. So that gives me V2 equal to 8 liters. And now, if you go back to the equation for the work done in isothermal process, nRT ln V2 over V1. We've got the temperature, we've got N, the number of moles, we have V2, we have V1. We can now use the equation to calculate the work done. W isothermal is nRT ln V2 over V1. That will be, the number of moles is 0.328, R is 8.314, T, the temperature is 293, times ln V2 over V1. You can see, again, I left them in liters. Does it make any difference? No, because it's a simple ratio. So I can leave it in any units as long as both are of the same unit. And that gives me the work done is 554 joules. That is the work done in that isothermal process. And we now need to find the heat added to the gas during this expansion. And what we now know is that the work done is 554 joules. dQ equal to dW plus du. And for an isothermal process, what is du? I should have asked you that. What is the change in internal energy for an isothermal process? An isothermal process is the temperature remains a constant. And internal energy is given by 3 over 2 nRT, where T is the change in temperature. Since there is no change in temperature, there is no internal energy change. Did you understand that? We said earlier that internal energy of a certain amount of gas at a very low density depends only on the kinetic energy. In other words, depends only on the temperature. If the temperature remains a constant, there will be no change in the internal energy. So what is the change in internal energy for an isothermal process? du equal to 0. So dQ equal to dW plus du, that reduces to dQ equal to dW. And we know dW, therefore the amount of heat added during that process will be 554 joules. I hope you now understand the method of solving these kind of problems in thermodynamics. All right. I think that will be enough for this lesson, and I will get back to you for the next lesson a little later.